So in this video, we're going to look at what's called the intermediate value theorem, or IVT. You are allowed to use the abbreviation IVT. It's just generally recognized to stand for intermediate value theorem. And the intermediate value theorem states that we have a continuous function on a closed interval. If you're going to appeal to the IVT in a problem, you must first show somewhere in your work that your function, it may be called f, it may have a different name, but that your function is continuous on a specific closed interval. If you do not do that, you cannot apply the IVT. So the nice thing in calculus is we don't have a huge number of theorems that are required for an AP calculus test that you have to memorize. However, the theorems that we do use, you must first show that you meet the hypothesis before you apply the theorem. So with the IVT, the important part here is that a function is continuous on a closed interval. If that function is continuous on a closed interval, then there exists a value c between a and b for those x values, such that f of c is between f of a and f of b. Now I know that that's like reading some foreign language for you. So what that means is if I have a continuous function on a closed interval, if I look at the y values of the endpoints, that what it's saying is I hit every y value between the two endpoints. This is actually one that if you've ever found a zero on a graph in your equation before, you've taken advantage of the IVT. So on our calculators, on the TI Inspire at least, if you graph something and you want to find a zero, it asks you to bound it to the left and to the right. So you're picking to the left where the function is positive and to the right where the function is negative, and saying that somewhere by the IVT, somewhere in between, the IVT says that the function must equal 0 there. Now, we have to practice two things with this. First, before we practice actually the conclusion, we have to practice the hypothesis. In that, here I have three different examples of functions, and I want to know just does the IVT apply? So, in this first example here, I have a function, and there's a hole in my function between 1 and 2, so this is not continuous on that closed interval 1 to 2, so no IVT for this one. There's no point in me even going any further because since the hypothesis doesn't work, the conclusion is there's no point in looking at the conclusion. If I go to the purple graph here with f, I can see I have a hole again. It is at 1, however, it is continuous from 1 to 2, but it's not continuous on the closed interval from 1 to 2. And that's, again, the important part here is this is not continuous on that closed interval from 1 to 2. So again, no IVT is allowed. If I look at the blue one here, I see there is still a hole, but if I'm only looking from 1 to 2, it is continuous on this closed interval from 1 to 2. And so I am allowed to use the IVT. So the IVT does apply. So hopefully that gives you a good idea of just how we go about looking to make sure the hypothesis works. So now if we look at dealing with all of this together, and there are going to be kind of two ways I look at this. One is going to be algebraic and the other with a table. So algebraically, here I have a function x squared over x to the 7th plus 1. And I want to show that this function has to have a value of 0.4 for some x between 0 and 1. Well, if I look at this function, there is a discontinuity where x equals -1, because at that value I'd have 0 in the denominator and I'll actually have a vertical asymptote. However, that doesn't affect the interval we're looking at, so f is continuous, and this is f, on that closed interval from 0 to 1, so the IVT does apply. So what I then need to do is look at what are my endpoints. So if I plug in f of 0, or I should say plug in 0 to find f of 0, I'm going to get 0. If I plug in 1 to find f of 1, I get 1/2, which is 0.5. And since f is continuous on the closed interval, the IVT applies, so we know the function does hit every y value between 0 and 0.5. So we can say, yes, f of x does equal 0.4 for some value in that interval from 0 to 1. Now, please note, it doesn't care what the x value is for that. It just wants us to show it has to happen. If we look at a tabular way of doing this, so here I'm not actually given an equation for f, but I am given some values for it. And most importantly, I am told f is continuous. So IVT does apply for the entire interval that this table covers. So if I first want to say, does f of x equal -7 on the interval from 0 to 12? Well, I start at -2, I go up to 5, then up to 76, then down to 0. What I can say is I know from that because f is continuous on this entire interval, it's also continuous on these smaller intervals. So between 0 and 4, we do hit every y value between -2 and 5. Now, -7 is not in that, so I can't say it there. From 4 to 8, I hit every y value between 5 and 76. Well, again, -7 isn't there, so it can't be in that. It doesn't have to be in that interval. And then from 8 to 12, I have to hit every y value between 76 and 0. And again, -7 doesn't show up in that interval. So I would have to answer that no, f of x is not guaranteed to equal -7. Now it might, because I don't know how f is behaving between x equals 0 and x equals 4, or x equals 4 and x equals 8, etc. But based on the information I have, the IVT, and the fact that f is continuous over this entire interval from 0 to 12, I can't say that f is guaranteed to. But if we then ask, does f ever equal 20 on this interval, we can actually say yes, because between x equals 4 and 8, the y's have to go from 5 to 76, and from 8 to 12, the y's go from 76 to 0. So I can say here that yes, f of x does equal 20. On that interval from 0 to 12. And we could even be more specific and say it's on that interval 4 to 8, or on the interval 8 to 12.